Scientists tell us that the world is warming, and although there's much uncertainty regarding the extent of the warming and its consequences, there is broad agreement that a warmer climate will affect weather, sea levels, ecosystems and agriculture.
Clearly there's a lot of uncertainty about the future, and I suppose the uncertainties come from different things. It's uncertain what the future concentrations of greenhouse gases will be, and then it's uncertain how the Earth, if you like, as a system will respond to that warming.
How do we make decisions about our environment when there's so much uncertainty? Climate change science offers us no simple answers. However, using statistics, we can build upon our assumptions using rational methodologies to arrive at meaningful recommendations.
Climate change has been happening for eons. So I think the question that society probably cares about is whether climate change caused by emitting greenhouse gases is real. There's been a lot of research in the last 2 decades that's really been able to say pretty definitively that humans are contributing to the climate change that we're experiencing today.
Lara Koopers is one of many scientists documenting changes in our planet's climate and its effect on ecosystems. Climate change is not a new phenomenon, but what is new is the rate at which it's changing.
You know, you think of the difference between a slowly rising tide and a tsunami, right? And that's sort of the difference between maybe climate change under natural historical conditions and climate change that we're projecting over the coming decades and centuries.
Climate change is most visible where water meets ice. This is where a small change in temperature has the biggest effect.
We see a lot of evidence of climate change in these cold environments, and we've seen it early there and we've seen it very strongly there.
Nowhere is this effect more visible than in retreating glaciers.
Retreating and shrinking glaciers are the single most tangible evidence of climate change in the world today, and that's what our cameras are capturing. We have cameras in Alaska, in the Rockies, in Greenland, in Iceland. We've been watching glaciers in the Alps and in Bolivia, and so we're seeing the same story everywhere. 95% of the glaciers in the world outside Antarctica are retreating and thinning and shrinking.
There's also strong evidence that as ice melts and temperature rises, sea levels are rising.
What we find here in this dock, in this area, is that sea levels have been rising at 1.2 millimetres per year since the 1930s. In fact, the last 2 decades, they've been rising rather more rapidly than that. But we do see a definite rising trend in sea level here in Southampton, and we see rising sea levels around most of the UK. And the explanation for that is that the ocean volume is growing, and the way to explain that is that the oceans are expanding as they warm, and also that land-based ice is melting and flowing into the sea and increasing the volume of the ocean.
How much will the sea level rise? The estimates vary, but it could be as little as half a metre, but it could be that if the whole of the polar ice cap melts, the water could be lapping around on the road of the Golden Gate Bridge.
But studying the visible effects of climate change are only part of the story. Many scientists are trying to understand how a changing climate will affect the complex interactions among plants and animals within ecosystems. At nearly 3,500 metres above sea level, pine forest gives way to a community of plants that makes up alpine tundra.
What we're really interested in is how the overall landscape is going to change. And with warming temperatures, we think that they may be forced to move upward in elevation, but we're at the top of the mountain nearly. A number of people have developed computer models that predict that a lot of these species that are growing at these high elevations may be very challenged to make it essentially as the climate warms, and their habitat might be pushed sort of up and off the tops of the mountains. And so we're experimentally essentially testing some of those models that people have developed.
Lara Koopers' researchers are heating small plots of seedlings through the winter and summer to document the effect of future temperature changes on pine tree germination and growth.
So the infrared heaters here are causing the snow to melt earlier. There are plots right nearby around this one that don't have infrared heater arrays, and they're still covered in snow. If they had the heater arrays, they'd also be melted out, but because they don't, they're still covered. Basically, we've sown these seeds into these garden plots, and some of the plots we're experimentally warming with these overhead heater arrays, and others we're just leaving to be what we call control plots to get at the key question of whether climate change is going to affect the ability of tree species to get established in the tree line. But there's some really healthy seedlings in here that have survived over the winter. They germinated last year, and so it's not surprising, that if you sow a seed, the plant will grow. The question is, how are the probabilities changing across the sites and with the warming climate?
One of the problems for scientists trying to understand the effects of climate change is that this change occurs over long periods of time, and few have the luxury of studying change over a lifetime. One scientist who recently found himself in the centre of climate change debate is James Thomson. For 20 years he's been studying a small perennial that blooms at high altitudes.
High elevations pose some special problems. This is where we might first see things like species doing poorly because the situations have changed. Essentially, I've asked a very simple question: what causes a flower to be a success? Does it get pollinated? Does it set a fruit? Does it make seeds? How many seeds does it make?
What he's discovered is that as the climate warms, the snow melts earlier, causing the glacier lily to bloom earlier.
Basically, these require a visit from a pollinating animal to succeed. But there is, unfortunately, a deterioration in the pollination service they're getting. The flowering is tending to happen earlier in the spring because the snow is melting faster than it used to. And I think this is some manifestation of a climate change effect. This is a plant that might be subject to getting dislocated in time from its pollinators. And in fact, that seems to be happening.
Scientists like James Thomson are finding that the effects of climate change are both subtle and profound, affecting many species and ecosystems in ways that as yet we do not understand.
If climates are changing, relationships between plants and pollinators and other mutually beneficial relationships, those may be disrupted. These glacier lilies are a cog in a pretty complicated ecosystem, and maybe not a trivial one.
We don't know how many species and how many ecosystems are affected, and we're uncertain about the consequences of these effects.
Little differences in how individual species respond to climate change tell us something about how the whole biosphere is going to respond to climate change. And so species here and there ultimately sort of come together to tell a fuller story.
While this fuller story continues to unfold, there remains much uncertainty for policymakers who face two approaches to climate change.
In principle, we could try either to prevent global warming or we could try to adapt to it.
We're going to have to be doing some, what I would call adaptation to the effects of the inevitable climate change. But then I think mitigation is important to limit that change to what we can manage. I think we need to do both. We need to try and reduce global warming by reducing less greenhouse gases, but we'll need to adapt to the changes that result from those we have emitted.
Preventing climate change, or mitigation, requires new technologies and global action to reduce gas emissions, both of which are uncertain. So in this film we ask, how can we make sensible decisions about adaptation to climate change? The sea level is rising, weather patterns changing, agricultural zones are shifting. How can we make sensible decisions about where to focus our limited resources to best adapt to climate change? One way of looking at these problems is to apply monetary values to the costs and benefits of adaptation, and then use statistical methods to make sensible decisions about where to focus our limited resources. But before we can do that, we need to consider a concept that we call discounting.
People prefer the current to the future. We know this
because you have to pay an interest rate. If interest rates are 5%, people are saying, I'm indifferent between £100 worth of benefits now and £105 worth of benefits in a year's time.
The future is worth less to us than the present. We can work out the discounted value of some sum, the present value, PV, for any interest rate for any future time period. And we use the formula that PV, present value, equals A over 1 plus R to the power n, where A is the sum of money we're talking about, R is the appropriate interest rate, and n is the number of years into the future that we're considering.
Suppose we had a 10% discount rate. We're saying that we're indifferent between £100 now or £110 in a year's time. Or to put that another way, we'd be indifferent between £82.6 now and £100 in 2 years' time, because if we had £82.6 now, we could invest it at a compound interest rate of 10% and turn it into £100 in 2 years' time.
Our table shows us the present value of £1 at various interest rates in 200 years' time. We're looking at a period well into the future because global warming policies will continue to have an effect for a very long time. Given a discount rate of 5%, the present value of £1 received in 200 years' time is only 0.000058 pounds.
On this basis, we might argue that you'd have to love your grandchildren a great deal if you're willing to give up, at say a 5% discount rate, £10,000 now so that they could have 58 pence in 200 years' time.
Discounting is a well-established idea that's useful in making investment decisions. For instance, using discounting to make decisions on motorways or high-speed rail lines makes sense. But does it make sense when considering adaptations to climate change? Some think so, but not all would agree that it does.
Well, public policy is all about values. And it's essentially saying that as people who live now, we care more about the wealth that we're going to accumulate.
There are other problems with discounting. You might feel that climate change raises ethical issues because costs are not borne within an investment cycle, but by future generations. You might be concerned that costs of adaptation are not borne evenly by all societies. For instance, European nations are already preparing for sea level rise and will suffer relatively minor effects, whereas some nations may be completely inundated. Sea level rise in Europe is an engineering challenge, but for other parts of the world it may obliterate nations and cultures. Similarly, damage to habitats in mountains and coastal regions will cause extinction of many species. Any value we assign to this will have large uncertainties attached to it.
There are further problems when we think about the distributional effects. Suppose there's some policy which is going to lose $1 per day per person. It's pretty trivial. Unless you're a developing world farmer, in which case it might mean the difference between life and death. We'll return to the question of the distribution of income in a later film. There are no right answers here because we're not always agreed about the costs and the benefits involved. But what we are interested in is the methodology. So let's look at some estimates that have been made, but not get too hung up on the numbers. Let's just understand the methodology. Given we're so unsure about the risk factors, we'll proceed here on the basis that we're dealing with uncertainty. So how do we make a rational choice when we're so uncertain about the future? There are 4 possible decision rules, and the first one we use is the principle of insufficient reason. That says we have no sufficient reason for thinking that one outcome is any more or less likely than any other. So we'll attach an equal probability to each of the outcomes. In our case, we have 3 possible outcomes, so we'll attach a risk factor of 1/3 to each possible outcome.
To illustrate the approach, we'll simplify and have just 3 possible scenarios. The first we've labelled optimistic, where we assume that the effects of global warming will be relatively small and benign. Pessimistic, where we assume that the effects of global warming will be relatively large and damaging. And medium, where we assume something between the other 2 possible outcomes. We have 3 policy possibilities as well. Strong, where significant policies are taken to modify presumed global warming damage. Weak, where little is done. And moderate, where some policies of a fairly limited nature are undertaken. The values in the table show the annual percentage loss of world income, gross domestic income, associated with each outcome. Don't be fooled by the apparently trivial numbers. World income amounts to many trillions of dollars, so each percentage point represents a severe loss of well-being. Notice that on an optimistic scenario, it would have been better to have a weak policy or maybe do nothing. This is because the damage would have been small anyway, and we've wasted scarce resources dealing with it unnecessarily. So how do we make a rational choice of policy when we don't know for sure the seriousness of the damage of global warming? We'll look at 4 possible strategies for making a choice under uncertainty. The first strategy is to use the principle of insufficient reason. This principle is that we have no sufficient reason for thinking one outcome to be any more likely than any other, and on this basis we attach an equal probability to each outcome. In our case it will be 1/3, and proceed as if we were in a situation of risk with these known possibilities. So the expected value, EV, of a strong policy is EV will be 4.5 times 1/3 plus 3.5 times 1/3 plus 2.5 times 1/3, which equals 3.5. So with a strong policy, the expected value is 3.5% of loss of GDI annually. Then with a moderate policy, the expected value will be 2.5 times 1/3 plus 3.0 times 1/3 plus 3.5 times 1/3, which equals 3.0. And with a weak policy, EV comes to 2.0 times 1/3 plus 3.0 times 1/3 plus 7.0 times 1/3, which equals 4. So given that we're trying to minimize the damage, a moderate policy is optimal, taking some steps, but accepting that the cost of some steps is greater than the expected benefits. Of course, if the risk factors are known, we could work out an EV using those values. So if it's agreed by the scientists that the pessimistic forecast is much more likely, we could rework using these weights to get a new EV. A second possibility is suitable for the optimist. This is sometimes called a maximax policy. Assume that the best will always turn up. So looking at our table again, here we presume that if we pick strong as our policy, then we'll lose the least income, only 2.5. For moderate, we'll also lose 2.5 because we assume an optimistic outcome. And for weak, 2.0. So given our optimistic assumptions, minimizing the loss requires us to choose a weak policy option. We'll choose that and optimistically hope that we only lose 2% of GDI per annum. A third possible strategy is suitable for the pessimist. Assume that the worst will always turn up. So looking at our table again, here we assume that if we pick strong, then we may lose 4.5. That would be the worst possible loss of income. For moderate, we might lose 3.5, and for weak, as much as 7%. So minimizing the loss requires us to choose, in this case, a moderate policy option, because the worst we can then lose is 3.5% of annual GDI. So that's our Maximin strategy, as it's called.
There's one more approach to consider. With an issue like climate change, if we get it wrong, it could be extremely serious. So we may want a particularly cautious approach. Then we might want to use the minimax regret approach. The essence of this approach is to look at the extent to which we might regret any particular choice we've made, and then pick the option which minimizes the regret that we'll have.
Returning to our table, we first construct a regret matrix. For each policy, we ask, what's the maximum regret that we could have? If we pick a strong option and the optimistic forecast is correct, we lose 4.5% of GDI, when by picking weak, we could have lost only 2%. The regret we have is therefore 2.5%, the difference between what we got and what we could have had. If average turns up, we regret picking strong, but only by 1/2 of 1% of GDI. If pessimistic turns up, there'll be no regret at all. I can perform that same operation for moderate and weak policies, and then that gives us our regret matrix. Our policy strategy is now to minimize the maximum regret. If we choose strong, our greatest regret would be that it's cost us 2.5% of GDI. For moderate, 1%, and for weak, 4.5%. So minimizing the maximum regret requires us to choose, in this case, and under these assumptions, a moderate policy.
Of course, the policy recommendations we've come up with depend upon the uncertain assumptions that we've made. There isn't a right answer that we've found, but if we understand the statistics, we have an approach which is suitable for examining problems either in the public or the private sector when there are issues of uncertainty involved.
Scientists continue to refine climate change models. The evidence for global changes continues to mount, and scientists are beginning to document not just the global effects, but the small local changes that enhance our understanding of local effects and consequences. As our knowledge improves, the uncertainty may well diminish, and it will be possible to make more precise policy recommendations using statistical methods like these we've examined.
There's always the possibility that we might see really very large changes, and I think in a sort of risk management sense, those large changes are worth avoiding. And the world's a stress system already. I think it's not just climate change impacting a world without other problems. It could be the straw that breaks the camel's back.
I'm regularly surprised by how sensitive the Earth system, the biosphere, is to what we might think of as pretty small changes in the climate.
I see these as important challenges that if we ignore them and put our head in the sand, then we're going to live in a pretty frightening world. But as long as we keep our eye on these issues and we don't ignore them, then I think society should be able to adjust and deal with them. But the sooner we can act, the easier it will be to do something.
We think we know a lot about the natural environment, but every year there's a new surprise. And I don't know what it'll be this. I don't know what it'll be this year, but I'm sure there will be one.